So in this video, we're gonna talk about a crystalline or the crystal structure. So let's imagine we're gonna have a cross section of some random crystalline material. And you can say that this is the two-dimensional representation of a crystalline material. And we know that crystalline is the structure that created based on the arrangement of atoms in a particular pattern that is repeated in all directions. And you can pick any pattern that you want. So let's say I want my pattern to be a square box that connect the four atoms together. So in order to make a complete crystalline, we need to duplicate or repeat the square box in all directions. So I'm gonna repeat it and so on. And this single square box or the pattern that you use to make a complete crystalline material is called a unit cell. So basically, unit cell is a pattern that you're gonna repeat it and duplicate it in all directions to make a complete crystalline structure. And since our unit cell is a square box of four atoms in each corner, we can call this crystalline as a square box lattice. So square box lattice means your crystalline structure is made up by a bunch of square unit cells. And if I have a crystal solid that make up by a bunch of, like, let's say diamond shaped unit cell, and they all look the same across in all directions, then that structure can be called as a diamond lattice. So whatever shape of your unit cell, you can put it before the term lattice. So let's have one more example. So in this example, our unit cell gonna have the shape of a parallelogram. So parallelogram gonna look like this. So let's apply the unit cell into this crystalline object, and then we're gonna duplicate it across all directions, and so on. Therefore, this crystal structure can be called as the parallelogram lattice because it's made up by a bunch of parallelogram cell units. And another definition that you need to know, those atoms right here, you can call it at lattice point. So I already showed you the lattice structure concept in the two-dimensional representation. But in real life, our crystal solids always have a three-dimensional shape. Therefore, it's gonna have a 3D lattice. And since different crystallized solid is make up different type of 3D unit cell, which will be shown more details later on, but then for now I'm gonna just show you a more generalized 3D unit cell. And this generalized 3D unit cell needs to be duplicated and repeated across all directions in order to form a complete crystal solid. And as a reminder, those blue circle right here represent for the atoms, or you can call it at lattice point. And we can also determine the position of those lattice points by using a vector. So I'm gonna pick this lattice point right here as our reference point in order to form our own, like, 3D coordinate system. And from this point, we can have our first vector. Let's call it A, going to this direction. And also from this, we can have our second vector, which I'm gonna call B. And lastly, we're gonna have the vector called C in the upward direction. So now let's express the position of the lattice based on those three vectors. So I'm gonna call the position of those lattice points as R vector. And we're gonna have P times A vector plus Q times B vector plus S times C vector. And P, Q, and S are integer number, and they are vary differently based on the position of different lattice points. So let's have some example. Let's say you want to find the position of this bottom lattice point. And since it's only lie in the A vector, therefore it doesn't have the P and the C component. So let's call R bottom gonna be P times A, where Q and S gonna be 0 because this lattice point only lie in the A vector direction. So how about this lattice point? And let me call it R bottom 1. And since this point lie in the plane that make up by the B and A vector, therefore the position is always depend on the B and the A component. It doesn't have the C component. So we're gonna have B times A vector plus Q times B vector, and the S gonna be 0 in order to hide the C component. And you can draw more on other vector on the top or anywhere you want. And also, if you want to find the length between two lattice points, let's say from this one to this one, you can use the notation A, and it's look different from the A vector. The A vector has the arrow sign on top, but for this one, it's only have the A letter, which means it stands for the magnitude or the length between those 2 points. So you want to call the length between this point and this point, just call it C. And similarly, from this point to this point right here, you're gonna call B. So we already know how to name your vector, which is A, B, C, and also the length between the two lattice points, A, B, and C again, without arrow on top. So how about the angle that form between your vector? Let's say the angle between A and B, the angle between B and C, and the angle between A and C. So from A and C, we're gonna call it alpha, and from B to C, we're gonna call it beta, and lastly, from A to B, we're gonna call it omega. So those three gonna be the notation that you're gonna use to name the angle that form between your three vectors. So in real life, there are a total of 7 lattice systems, which is gonna show in the image right here. 1, 2, 3, 4, 5, 6, 7, and each lattice system contribute from 1 to 4 unit cells. So on the right side, the total of unit cells that you can find is 14. And this table right here is called the Bravais Lattice. And there are a total of 14 Bravais Lattice that you can find, which is on the right side. And Bravais Lattice is named after the French physicist called Auguste Bravais. And you can use those properties, which is A, B, C for the length, and alpha, beta, and omega for the angle, and you plug it to your generalized case in here in order to form the Bravais unit cells. And in the next video, we're gonna talk more details about the top 3 unit cells are under the cubic lattice system.